Okay, so we've spent a lot of time setting up and observing simple RC circuit. Okay, there's some resistance which we kind of believe is unknown, but you kind of read it off. You got voltage and current readings, okay? And you got them simultaneously on your screen. You've got screenshots. One person didn't think to bring the computer today. I actually left home, got halfway here, realized I'd left the computer behind. So main reason we're doing this video is so I can use the computer since I went back home. Okay, wanted to be about 10 minutes early. I just made it about 2 minutes. Okay, so anyhow, here we've got this RC circuit. Then we got a voltage. It's basically square wave voltage. Now we're doing that by hand. We're switching some leads from a battery. So we played around with these things with the generators and reversing the generators to get a feel for it, because I think that gives us a firmer connection to what's going on. Okay. But if we want a smooth output to our interface, we're going to need to use a smooth source. And these generators are great, but they're not that smooth. Okay, so in any case, we varied the period of the frequency of the square wave. Okay, so if we have a low frequency, square wave kind of looks like this. Okay, then of course it'll go down below the axis and do this. If we're looking at the magnitude of the current versus time, graphs could look something like this. We never had a graph that looked exactly like this. Yeah, if we used a bigger resistor, we could have slowed things down. Well, that might have happened. Okay, but there's a limit how fast we can manually switch the leads to give us an alternating wave. The magnitude of the current is not down here. The magnitude is up here, even though the current is down here. Okay, so I think we understand that pretty well. Okay, so here I just drew the magnitude. Now we go down like this, and I go down here and up here and down here and up. And you want to understand what's going on. You want to think about what's happening. We talked a lot about what happens in a circuit. Whatever the voltage is here, it's going to tend to create a current in this direction or this direction, which pulls charge off of one plate, puts it on the other. And we get a certain voltage across the capacitor, okay? And the charge on the capacitor tends to, well, has to, if we're pulling positive charge off of this plate, okay? That means that the voltage here is at that time negative, okay? And we're creating negative charge here by pulling positive charge off and by depositing the positive charge over here. We get a negative push from the capacitor, which opposes the push of the source. And then when we reverse, well, you want to think through and you want to understand that in detail, because everybody here has at least done Laplace transform their differential equations class, and you have the tools to analyze what happens with the square wave. And it's not particularly difficult. Okay. I mean, if you understand the Laplace transform, that's not a prerequisite for this course. I just mentioned it because everybody has that background. Okay, well, we come back to Earth here. And what I've asked is that people estimate the average magnitude of the current. If, of course, this is 0 here, and this is 0.6 here, and it's amps, okay, 0 to 0.6 amps. And in both cases, that's our scale, and our maximum is like We're going to assume the maximum is 0.6 amps. It's about what we saw. Okay, so we asked, can you estimate the average current? Okay, and we got estimates of 0.25 or 0.3 up here. Okay, so that would mean that the average current would be maybe around here. Okay, now is that a good estimate of the average current? Well, it is if the area above our average is equal to the area below our average. Looks like that's reasonable. Pretty reasonable to me. Looks like this area is a little bit less than this. So maybe I should have drawn that line up a little higher. But still, we get the idea. Okay. So if you thought it was 0.25, and that's really your shape, because with our estimates were like 0.25 and 0.3. If you think it's 0.25 amps, then maybe you're a little low. If you think it's 0.3 amps, maybe you're a little high. And you've got your screenshots. You can take a closer look at it and see what you think. And then we'll compare that to the model that we get, because we can do the model, because it's really based on a little pre-calculus and a little calculus. We're going to do that model. Okay, so 0.6 here, and well, our average is everybody had either 0.5 or 0.52. Okay. As I comment, it's really 0.5208376. I can see these things better than you can. Yeah, just visually. Yeah, right. Okay. So maybe it's here, and the area down here might be about the same as that area out here. Maybe not. I think it's fairly close. So maybe the average is 0.27. If that's 0.25, and I don't know that it is, I didn't scale this all that carefully, but it kind of looks like that'd be about 0.25, about 4/10 of this. Okay. We'll say 0.27 and average here. I'll say 0.51 because that's kind of what you get if you round the average of your estimates, and I can't implement that. Not from this picture. Okay, so that's all good, right? Now we see that we get a higher average, the greater frequency. So your average current is closer to your max. And your max in both of these cases was about the same. So you're producing greater average current here than you were here. I'm going to say the low frequency is getting filtered out. You go to lower and lower frequency, well, the exponential decrease has a lot more time to approach zero. Approaches zero much more closely than the average. And that's pretty much what it's told you. Okay, so I think you have a pretty good handle. Now let's get a little more rigorous. And let's say that this is an exponential decrease. We'll use numbers. Okay, you got 0.6 amps here. And your time here is, let's say, 10 seconds. Then what's your exponential function? There's various ways you can do it. But what I want you to do is pick a point out here where you think you have a fairly significant change in time, but you can read the current with pretty good accuracy. And where both the time and the current have significant changes, okay? If you have too much change in the time, it gets hard to estimate the current from this curve. If you have too little time, if your time's too low, then it's hard to estimate that time. So estimate a good point on this graph, and that gives us 2 points on a graph, and we can easily then calculate the exponential function and its average value, and that's what we're going to do. So write out the coordinates of a good estimate of, well, write out the coordinates of a point where you think you get a pretty good estimate of both time and current. Okay, now everybody has pretty good estimates. So some people need a little more concavity in their graph. They got a good exponential function. I'll show you how to sketch a good exponential function in a minute. Let's just go along. You tell me where to stop, and I'm going to estimate the coordinates of the point. Okay, I think that's a perfectly good point. Project down here and across. Well, I can put a scale in this. I probably should use 8 seconds here or something. It's easy to cut 8 in half a bunch of times. Then I'm going to cut 10 in half, and that's going to be above here. That's going to be 5. Well, if I cut 5 in half, it can't be above there. So I'm going to say that's about about 2.7. That's one less than 3. And this, and that looks really pretty close to the middle. Okay, this distance and this, it's a little, if I'm doing it right, it's a little bit below the middle. So I'm going to say that the current I was really wanting to say 0.27, but I didn't want to be misleading about these coordinates being the same. Don't blame me for this. It's where you told me to stop. Okay. So now what do we have? We have current as a function of time is we'll say I naught E to the KT. One possibility, right? I naught B to the T. Those are 2 very standard forms of the exponential function. We could do I naught times 2 to the KT. Be a different value of K. But there are advantages to the power of 2 function. However, if we're going to do calculus with it, probably doesn't go with this thing. The algebra is actually easy with this. You just end up taking a root. Okay. But the algebra is not bad here, although you do have to change from exponential logarithmic form. So what we have then is I of 0. Well, actually, it's going to be I naught because T is 0, E to the 0 is 0. So it makes it fairly easy. And I of 2.7 equals I naught E to the 2.7K. Right. well, I naught equals I of 0, and I of 0 is 0.6. I of 2.7 is 0.28. That immediately gives us this equation. Plugging our information into this equation. Could have organized that a little better, but I'll leave it to you. I want you to do your own estimates, okay? It's actually very quick and very easy. Okay, so we have the point that the equation 0.6 e to the 2.7k equals 0.28. So that 0.28 divided by 0.6 is 0.4. I'll round it to 0.47. 4, 6 repeating. It's 4 2/3. 6 goes into 28 4 2/3 times. Okay. And that's e to the 2.7. Okay. So that, well, if we do the natural log of both sides, which is the efficient way to do it in pre-calculus, we just know how to change this to the equivalent logarithmic form, and either way you get the same thing. But I'll go with the natural log of both sides because we're probably going to see more of that in your curriculum than you will the pre-calculus inverse function idea. Although it's important to understand both. Okay, so the natural log of b to the 2.7k equals a natural log of 0.47, so that 2.7k equals a natural log of 0.47. This is also an inverse function. Natural log is inverse to the exponential function. So that k equals a natural log of 0.47 over 2.7. And that's approximately, natural log of 0.47 is probably in the order of negative 0.66 or so. Okay. Because natural log of 0.5 is like real close to negative 0.7. Okay. So that's going to be a little bit less, maybe 0.67. And you divide that by 2.7 and you get roughly 2.5, negative 2.5. So I'll ask you, because I saw some of you with your calculators working about 6 steps ahead of me, and I'd love to see that. Okay, actually, the natural log of 0.47 is more than the natural log of, has a greater magnitude than the natural log of 0.5, so I kind of missed that. So we get something approximately equal to negative 0.34. Okay, 3.4, sorry. No, 0.34. Okay. Okay, so now we know that approximately 0.6 e to the negative 0.34 t. Okay. So your time constants are reciprocal of this k. Time constants of time it takes to fall to 1 over e, which is 37%. And that would be roughly 3 seconds. Okay, well, if we go up to 3 seconds, that would be here. And is that down to 37% of 6? Yeah, 37% of 0.6 would be a little over 0.2. That's reasonable. Half-life, you divide 0.7 by 0.34, and you get like 2 seconds. Okay. And a 2-second half-life is pretty consistent with this graph. What's the average value? It's the integral from 0 to 10 of 0.6 e to the negative 0.34 t divided by the length of that interval. That's the whole idea of average value. That's how you calculate an average value. Okay, well, you know, you take your antiderivative here, and you're going to get 0.6 over 0.34 times e to the negative 0.34 t. Evaluating e to the 0.34 t at 0, you're going to get 1. Evaluating it at 10, it's going to be down pretty close to 0. So you can pretty much estimate that this is going to be 0.06 over 0.34. Okay. A little more than 0.06 over 0.34. 0.06 over 0.34 is like 0.17, a little over that's 0.2. That's right in the range of what you estimated for your average values. So one thing I want you to do, come back with it Monday, is calculate that average value and do it for your other pictures. Do a good estimate of a point and your maximum, maybe it's not quite 0.6, and see how the average current is changing as you double the period, okay, from 2 seconds to 4 seconds to 8 seconds to 16 seconds. Just 2, 4, 8, 16 successive doublings. Maybe make a graph of what the average value does as a function of the period. Quickly, that would be the differential equation. I mean, you know how to do the differential equation. Okay. And we'll talk about that Monday a little bit, although we're not really up to alternating circuits yet, currents. We want to get a pretty good foundation in alternating currents because you have the background for it. And at least 2/3 of the class wants to do electrical engineering. Okay. So